we will discuss about the gating system. Gating system consists of the pouring cup, sprue, choke, runner, gate, and riser. As you can see, this is the whole casting, all the features or the components of the casting. This is your pouring cup, and this is the sprue, and then finally there is a well, and to it your runner is connected, and then this is your side riser, and then this is your gate, and then this is the mold cavity under which this casting is formed. And I was talking about there are two types of riser. One is the top riser and another is the side riser. So in some casting processes you will observe that they directly feed the material from the top, and then that material reaches into the mold cavity. So there the sprue and the riser is a common thing, is a same feature. However, in case of this side riser, there is one pouring cup, and then there is sprue, and then after this is a whole gating system. So what's the significance of the gating system? So basically this gating system controls the flow rate of a molten metal into the mold cavity, and reduces the turbulence, minimizes the defects. So the gating system consists of the pouring cup, sprue, choke, runner, gate, and riser, and all these components have their own I can say significance. So the first part of the gating system is your pouring cup or basin. The pouring cup is the first point where your molten metal is poured, and it is in the form of a cup, and it is of two types. One is the manually cut pouring cup or the pouring basin that is formed in the core part of your molding box, and then the second type is made up of ceramic material. So ceramic material are refractory material, and they can be used again and again, and they are also good in feeding the material properly. They control the flow rate, and they are available in different shapes and sizes. It has been observed that many times whenever you pour your molten metal into the pouring cup, then you can say vortex formation. So due to that vortex formation, the turbulence is created in the molten metal, and due to that turbulence, the atmospheric gases can trap inside molten metal. So vortex induces the turbulence, and that turbulence can damage the sprue wall or runner wall or mold cavity. So that turbulence can be surely be avoided with the help of this anti-swirl production. So these are some, you can say, the protruded part coming out into the inner side of the pouring basin, and this helps in breaking the swirling movement. So this is the advanced type of pouring cup, which is used to prevent the turbulence or this vortex formation during the flow of molten material. Then after this, the another part is the runner, that sprue part. So sprue we have studied in much detail, and what should be the correct size of your sprue, and how much area should be there at the top of the sprue and the bottom of the sprue. And then after this, so this is the pouring cup or the pouring basin, and then there is the sprue, and this is the you can say the opening or the first part of your sprue, and this is the bottom part of the sprue. The smallest area which is known as a choke. As the name suggests, the choke is to create a choking effect. So this section or this smallest area is known as the choke, and it slows down the flow of molten metal to prevent the aspiration effect in sprue. So we have already studied that if the sprue is of straight shape or cylindrical straight shape, then there will be a sudden flow of material, due to which there is a pressure difference, or you can say the lowering of pressure will take place in the liquid column, and which results in the aspiration effects, which means the, you can say, entrapment of gases and atmospheric oxygen inside the molten metal flow. In order to reduce that aspiration effect, you have to reduce the cross section of your sprue, and this reduced area is known as the choke. And we have already calculated this choke area with the help of Bernoulli's theorem and continuity concept that we have already studied in our previous lecture. We have calculated this expression that this third, you can say, the 0.3 is the region of your choke, and the velocity here can be calculated with the help of your Bernoulli's theorem, and here which is equals to root 2g h, and h is the total height, this is the ht, and then volume of flow at the choke area at any time can be calculated with the help of this AC, VC and T, where AC is the choke area and VC is the velocity of metal flow at the point 3 and T is the time. And this volume, or you can say the discharge flow rate, can also be rated by W by rho, where W is the mass of the poured metal and rho is the density of the liquid metal. Now, by equating these two equations, we can easily calculate the choke area in terms of the mass of the poured metal and the velocity of the molten metal flow at point 3. So it comes out to be this W by C. C is your coefficient of discharge. Now, why this coefficient of discharge is coming, that there will be different type of losses, and such as frictional losses will come into picture, and this coefficient of discharge will play its part in this equation. And the coefficient of discharge is there, then VC, you already know that it is equal to root 2 GST. So now you replace this term VC by root 2 GST. So your final expression of choke area will be W by C rho T under root 2 GST. So this is very easy to calculate the choke area. Then after this, another component is known as the sprue well. So it is located at the bottom of the choke area, and its function is used to catch and trap the first metal impurities. So you all know that during the melting of metal, the impurities will float on the surface, and many times oxide layer will also form. And if there is no trapping mechanism in the gating system, then all those impurities will flow inside the mold cavity, and which will produce the defective casting. The sprue well is particularly an area where you trap the metal impurities, and here if you directly pour the liquid metal into this pouring basin and then you directly feed it into the runner, so due to the high kinetic energy of molten metal, the erosion of runner wall and mold wall takes place. So in order to reduce this erosion effect and to trap the metal impurity, this sprue well is formed inside the gating system, and there is a thumb rule that sprue well area must be 2 to 3 times the choke area. So this is the thumb rule. And after this, the channel through which the molten metal flows is known as runner. This is the channel which carries the molten metal from sprue into the mold cavity, and generally the cross section of runner is taken as the square, and it may be 2 to 4 times the area of the choke, and that depends upon the gating ratio. So gating ratio we'll discuss in some next slides. And as of now, you should remember that this is a general rule that the runner, you can see the cross section should be taken as 2 to 4 times the area of the choke. And there should not be an abrupt change in the direction of the runner. So just like you see here, you can see there is a abrupt change in the direction of the metal flow. So that should also not happen, because it may also induce the turbulence effect. And if it is happening, then you should fillet the channel. You should make a curvature in the channel of the runner. And its length also should be short. It should not be more, and it should be about 4 times the size of the gate. So gate is the last component of this gating system, and it is an opening into the mold cavity through which molten metals into the mold cavity. We will discuss in the next slide what is a gate. So the gate is the portion of the runner through which the molten metal enters the mold cavity. So here you can see there are 3 different types of gates, and this is your mold cavity, and this point is known as the gate through which your molten metal, it comes from the choke area. This is the sprue well, this is the runner, and then here it will be a gate, and from that gate all the molten metal will flows into the mold cavity. As per the orientation of the gate, the gates are basically divides into 3 categories. One is the top gate, second one is the bottom gate, and third one is the parting line side gate. So the top gate, the gate is placed at the top surface or the top corner of your mold cavity, while in case of bottom gate, the gate is placed at the bottom of the mold cavity, and in the parting line side gate, the gate is placed at the center or at the parting line of your mold cavity. So these are 3 types of gates. And then after that, the last you can say the topic of this unit is the gating ratio. So gating ratio is very important term, and it basically controls the flow of molten material, and it refers to the relationship between the area of the choke to the total area of runner and the total area of ingates. Mathematically, it can be written as AC is to AR is to AG, where AC is the choke area, AR is the runner area, and AG is the gate area. And this gating system controls the molten metal flow, and based upon the area or the size of these three different types of choke and runner and gate, the gating system can be classified as pressurized system and unpressurized system. In pressurized system, in the gating system, right from the choke to the gating, it is gradually reducing. So here, first of all, there will be a choke area, and then the runner area will somewhat reduce, and finally the gate area will be the minimum. So in this case, the material is being pressurized, and the molten metal will have a maximum pressure at the exit of the gate. And in unpressurized system, the area will be gradually increasing right from the choke to the gate. And you can say this pressurized system is mostly used for reactive metals like magnesium alloys, etc. While as pressurized system, gating system is preferred for all other metals like brass, steel, aluminum, and these alloys, etc. And by looking to the gating ratio, you can easily see that what type of gating system is this. So a gating ratio such as 1:2:1 or 1:0.75 to 0.5 refers to the pressurized system. Here you see the area or the area of this choke, riser, and the gating is getting reduced, while as in case of the gating ratio is 1:2 or 1:3 or 1:1:3, it refers to the unpressurized gating system. So both the gating system has its own advantages and disadvantages, and for that you have to refer the books, and you just have to remind that the pressurized system is used for reactive metals like magnesium alloys, because these magnesium alloys are highly oxidized and they should be fed under the pressurized, you can say, the gating system, so that there should not be enough time of the magnesium metal to react with the atmospheric gases, and it should suddenly fill the mold cavity, and it should solidify it immediately. So that pressurized system is used for the reactive metals, and unpressurized gating system is used for all other metals. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.